Hello and welcome to Thermodynamics Part 2 lecture. This is going to be a very long lecture. You can't possibly sit down and listen to this video, watch this video, and stay awake or stay sane. You should have paper, pencil with you, something to write with, and a calculator, and prove each slide as we go. So let's begin right away. The objectives for this part of the unit are: 1, describe how evaporation affects a liquid's temperature, describe how condensation affects temperature, explain how evaporation and condensation can take place at the same time, describe how pressure affects boiling point, describe the effect of dissolving anything in a liquid on the liquid's freezing temperature, describe how something can boil and freeze at the same time. Explain why so few substances undergo regulation. Explain the relationship between energy and phase change. So what I would suggest is taking out a piece of paper and on each individual side put a different objective. So you have 8 objectives. I would put 8 sides of a piece of paper, 8 pages. And I would put at the top of each page, I would put the corresponding objective. And I would take notes from the video on each of those sides, depending upon what objective is being discussed at that time. Also, pay close attention to the example problems that I do, the quizzes that will take place the week that this unit begins will be taken directly from this lecture. So good luck, and let's begin. Bring water to a boil in a regular pressure cooker. Then remove the weighted cap so that steam expands violently from the nozzle. For drama, put your gloved hand in the path of the steam about 20 centimeters above the nozzle. Ask if you would dare to do the same with a bare hand. Then remove the glove and hold your hand in the stream. Caution, do not put your hand any closer to the nozzle. Amazing, actually the steam is quite cool. Acknowledge that your hand is not in the steam, which is invisible and is in the first 1 to 2 centimeters, 1 to 3 centimeters above the nozzle. Your hand is in condensed vapor, considerably cooled by expansion. So if you put a candle in the stream of liquid, you would find that the condensed vapor is really what you're looking at, would disappear, because the condensed vapor would go back into the gaseous state. When you see steam, that's not gas. Those are little tiny droplets of water. Those are condensed gas. Steam is colorless, odorless, clear, undetectable. You can't see it. It looks like air. You can't possibly see it. You can certainly feel it in terms of humidity, etc. But steam itself is invisible. And what you're actually seeing in condensed vapor is the little water droplets that it makes up. Here's a standard pressure cooker. And the way it works is this. As I increase the pressure, let's say that's the top number, 1 to 2. Well, that will increase the temperature below. So if I double the pressure, I'm going to double the temperature. And that's absolutely how it works. It's based on Gay-Lussac's law of gases. And as I increase the pressure, I'm going to increase the temperature. Gay-Lussac's law can also be compared to solids and liquids as well. As you increase the pressure on anything, you're going to increase its temperature. But that's how the pressure cooker works. You can cook a potato in a matter of minutes, whereas you'd have to boil it and it would take 10 or 15 minutes. You have to get the water boiling, etc. This is the phase change curve. Memorize this shape. The two plateaus are actually where the phase change takes place. And phase change, we will see, is a matter of potential energy. The greater the distance between the molecules, that is solids or liquids, the greater the potential energy that the material has to absorb. So when you're going from a solid to a liquid, it has to absorb energy. That's the heat of fusion. And you go from a solid to a liquid, you're going to increase the distance between the molecules involved. However, when you're going from a liquid to a gas, you're going to have a major absorption of energy. This particular graph is not drawn to scale. The amount of heat of vaporization is much greater than the heat of fusion. Energy is absorbed when change of phase is in this direction, and energy is released when change of phase is in this direction. And again, when you change phase, changing phase has to do with change in potential energy. That's all it has to do with. Change in phase has to do with change in potential energy. Now, what I was saying before is that the change in phase going from a liquid to a gas is enormous. The heat of vaporization for water, without looking at the unit labels, just for comparison purposes, is 540. And that for the heat of fusion is 80. So 540 divided by 80 is what? Well, 480 is 6 times 80 is 480. So it'd be 6.5 or 6.8. So it's the heat of vaporization is considerably higher. This brings to mind why steam can burn so badly. Steam, not only like 99 degree Celsius water is very hot, and 101, which is in the gaseous phase, steam appears more than 2 degrees hot because it contains 540 additional units of energy relative to the water. And we will see an example of this. Now, going back to the greenhouse effect from chapter 22, we saw that the greenhouse effect occurred, the reverse of the greenhouse effect occurred back in one of the ice ages when the ice sheet over the northern United States melted, formed this enormous lake in what is now present-day Canada. You see the outline of Minnesota, so that's the northern part of the United States. And then this giant lake occurred and busted and went into the North Atlantic, completely confusing the North Atlantic conveyor belt in which warm water comes up from the south, and it just diluted and changed the entire density structure of the North Atlantic and shut off that conveyor. What was left over in northern Canada was probably the largest inland lake in the history of what we would consider last 10,000 years, 100,000 years would be in northern Canada and part of the United States, and that was Lake Agassiz, and that was a giant lake south of the Hudson Bay. But this particular lake occurred south of the Hudson Bay and northwest of Lake Superior in northern Canada, and was the largest inland lake, larger than the Caspian Sea, larger than any of the lakes in the Great Lakes of northern United States. So I put this picture in just to show you how enormous that lake was, and that as big as that lake was, that was a remnant of the great flood that busted through and went into the North Atlantic and diluted all that water, shutting off the conveyor belt and plunging the world into another ice age. Okay, why does hot water freeze faster than cold water on a winter's day? Well, we have to look at this. This is actually drawn to proportion. You see that 540 calories on the x-axis there, and you see the temperature, and we're going to examine why water. It's actually going to be a problem right out of the book, and it will examine why hot water. So if you look at, let's say, 95 degrees Celsius, that's where our hot water will be. And why will that freeze faster than water that's near boiling? Well, it has to do with this particular idea, and that is that water will change to steam at very high temperature. So at 2 degrees Celsius, it will change to steam very quickly. At 98, let's say 98 degrees Celsius. And this will cause, if there's no external heat source, this 98 degree heat, this 98 degree water has to get the heat from somewhere. So it's going to get it from the rest of the water. So let's say you have 5 grams. Well, where's, it freezes. Well, it's going to freeze if and only if some of the water converts to steam. Okay, I'm going to take a break really quickly, and I would suggest you do as well. It's already 12 minutes in, and be right back. This is the generalized graph structure that you're going to have to memorize. Solids, liquids, gases, and gases. The flat parts are the changes in potential energy. The portion where the graph is slanted, you will have increases in kinetic energy. Okay, what we want to do is we want to do a problem. You remember that potential energy will increase as I go from left to right. You can see the molecules are close together in a solid, and they are farther apart in the gas. And the difference in potential energy will be examined going from solid to a liquid and liquid to a gas before we actually begin the problem in another 2 slides. The potential energy changes are as follows. The 80 kilocalories per kilogram and the 540 kilocalories per kilogram. You're going to have a temperature change of 20 degrees in the solid state, 100 degrees in the liquid state, and 20 degrees in the gaseous state. But it might, and then, so that's the general gist of it. You can read that very clearly by the graph. And the problem is, how much energy does it take to change 2 kilograms of ice at negative 20 degrees Celsius to 2 kilograms of steam at 120 degrees Celsius? And for future purposes, we will label the heats Q1, Q2, Q3, Q4, Q5. This will be precisely like the second type of quiz you will take in this unit relative to phase change. Here are the 5 changes, and the specific heat capacity of a solid, liquid, and gas can be taken from your equation sheet provided to you. So it'll be 2 times 20 times 0.492, 2 times 80, 2 times 100 times 1, 2 times 540, 2 times 20 times 0.83, and that will give you a grand total of 1,479 kilocalories to change 2 kilograms of ice at negative 20 degrees Celsius to 2 kilograms of steam at 120 degrees Celsius. So this, again, I can't emphasize more. Know how to do this problem. Know how to do this problem. These are some sample calculations taken from the conceptual development sheet. Number 4, a 50 gram sample of ice at 0 degrees Celsius is placed in a glass beaker that contains 200 grams of water at 20 degrees Celsius. How much heat is needed to melt the ice? And since there is 50 grams of ice at 80 calories required per gram, the heat would be 50 times 80, or 4,000 calories. By how much would the temperature of the water change if it gave up this much heat to the ice? Since the water gives off 1 calorie of heat for each gram, and for each degree Celsius, 200 grams of water gives off 2 calories for each degree change. If the water gives off 4,000 calories, it decreased by 4,000 divided by 200 calories per degree, or 20 degrees Celsius. What will be the final temperature of the mixture? Here we want to disregard any heat absorbed by the glass or given off by the surroundings in the air. If the heat needed to melt the ice all comes from the cooling of the water will cool from 20 degrees Celsius to 0 degrees Celsius. So both it and water from the melted ice will be at 0 degrees Celsius. So that's one of the problems that we have. A little confusing, but with some effort, please, again, ask me if you have any questions regarding this. This comes from the conceptual development sheet on this chapter. 1 gram of steam at 100 degrees Celsius condenses, and the water cools to 22 degrees Celsius. How much heat is released when the steam is condensed? Well, it's 1 gram, so it'll be 540 calories. How much heat is released when the water cools from 100 to 22? Well, it'll be 618. I'm not going to tell you how I got that. I want you to try to figure that out. And how much heat is released altogether? Well, 78 calories, since the water cools by 100 degrees Celsius to 22 degrees Celsius, or 78 degrees. Well, that kind of gives the answer away. In a household radiator, 1,000 grams, or a kilogram, 1,000 grams of steam at 0 degrees Celsius condenses, and the water cools to 90 degrees Celsius. How much heat is released when the steam condenses? 540,000 calories, since 540 calories of heat is released for every gram of steam. 1,000 grams of steam releases 1 times 540, or 540,000. How much heat is released when the water cools from 100 degrees Celsius to 90 degrees Celsius? 10,000. It's going to be since 1 calorie is released for each gram and for each degree Celsius. How much heat altogether? 550,000 calories are released altogether. Okay? I'm going to take another break, and I think you should too. I'll let you know when I think you should take a break and come back and finish. Number 9, sample problem number 9, simply says that, why is it difficult to make tea on the top of a high mountain? Because water boils at a lower temperature there, and it can get no hotter than its boiling point. Boiling point is dependent upon elevation and atmospheric pressure. How many calories are given up by 1 gram of 100 degrees Celsius steam that condenses to 100 degrees Celsius, 540? How many calories are given up by 1 gram of 100 degrees steam that condenses and drops in temperature to 22 degrees Celsius? That would be 618 calories. How many calories are given up by a household radiator when the steam when the 1,000 grams of 100 degrees Celsius steam condenses and drops in temperature to 90 degrees Celsius water, 550,000 calories. Actually very simple. These are not difficult problems. Again, similar to the quizzes that we'll have in this unit. This is a very simple cartoon. It shows the cycle of evaporation and condensation and how it simply you're reducing energy by you're reducing the energy of the material when you condense something. Evaporation excites it, then condensation cools it. So which is heating and which is cooling. This is just a great shot of a pig and a dog. What do they have in common? Well, they don't have sweat glands, and the pig cools off by rolling around in mud, and the water cools its body when it evaporates, and the dog pants to release water, and the water contains water vapor. The water vapor contains energy, so that's how it keeps cool, by panting. Neither have sweat glands. Now, you've all been hiking or camping or something like that, and you've seen canteens that may look like this. Well, why does that canteen have a cloth around it? Well, if you wet the cloth and then allow the water to evaporate, it's going to take. It's the only way it can evaporate is if it takes the energy from inside the canteen, and the canteen will get cooler. When you're hiking in the mountains or wherever, you can have cool water. You're going to feel chilly, right, when you step out of the shower. If you feel chilly outside the shower, still step back inside into the shower and be warmed by the condensation of the excess water vapor there. So, is the condensation, is that a cooling or a warming process? That's the question you have to ask yourself. Notice that some of these slides may have a motion picture camera on them. If you go to my website, you'll be able to see, on my school website, you'll be able to see the same cameras, and those indicate a link with a YouTube video. So you might want to do that. You have 6 different physical changes. You have sublimation, which goes from solid to a gas directly. You have freezing, melting, evaporation, condensation, and then deposition when you go from a gas to a solid. So you should already know these 6 changes, but it might be a good idea to understand that they have to do with the direction, the direction of the arrow. Solid to a liquid is melting, not freezing. Going from a liquid to a solid is freezing. This is regulation. In regulation, here's one of the misconceptions. Ice melts only when heated. When heat is added, ice can also melt under increased pressure. We know that when you ice skate, I've shown you that before, you're applying pressure to the ice, and the ice is melting, and you're actually skating on water, not ice. Or regulation, this wire that's connected to the weights will cut the ice, and then the ice will refreeze because of the latent coolness. We'll talk about that a little later. This is a very complex graph. It may seem rather simple and colorful, but if you can get this graph, you have graduated to, I know what I'm doing in thermodynamics. You have the 3 phases of water: ice, liquid water, cold water, and then water vapor, or the gas. And if you reduce the pressure, now pressure, what we know is pressure, it's about 101,000 pascals. So if you reduce it to 610 pascals or below, and then reduce the temperature to 0 degrees Celsius, that's called a triple point. That's where water vapor, liquid water, and solid water, ice, all exist together. Now, if you go below 0 and below 610 pascals, that's where, and then watch, see where the arrow is? Say it says here, move from left to right. It crosses that line and goes right into gas. So water can sublime to go from a solid to a gas without going through the liquid phase at very low pressures and low temperature. Now, this triple point diagram of water, you can use it for carbon dioxide. These come in all shapes and sizes for various substances. This is the triple point diagram for water. So at very low pressures and very low temperatures, water will sublime. We're up top. We're at the top of the graph. We have all three. This is the first major extra credit, how to make really crappy coffee. Thomas J. Crapper, one of my favorite people, and one of my heroes. And I want you to tell me about lyophilization or cryodesiccation. Explain to me in detail on an email, tdarcy17@gmail.com, how this works. Well, remember I said that if you reduce the pressure and temperature of a substance, you can change its properties relative to melting, boiling, etc. Suppose that a dish of water at room temperature is placed in a vacuum jar, as shown in figure 23.9, that's on the left. If the pressure in the jar is slowly reduced by a vacuum pump, the vapor pressure of the molecules within the water will be high enough to form bubbles, and the water will start to boil. The boiling process takes higher energy molecules away from the water left in the dish, which cools to a warmer temperature. As the pressure is further decreased, more and more of the faster remaining slow-moving molecules boil away. Now, let's examine and review what boiling actually is. Boiling is the conversion of liquid to a solid through a rapid form of evaporation. Now, for something to boil, its vapor pressure has to equal the atmospheric pressure. Now think of the atmospheric pressure caused by the enormous number of molecules at sea level. Well, that's a high pressure, 101,000 pascals. When you heat water, you're going to release water particles. And these particles will cause pressure. This is called the vapor pressure. And when the vapor pressure equals the atmospheric pressure, then it will boil. If the atmospheric pressure were lower, it would boil sooner. It wouldn't have to have as high vapor pressure. So there's a connection between vapor pressure and atmospheric pressure. Continued boiling results in the lowering of the temperature until the freezing point of approximately 0 degrees Celsius is reached. Continued cooling by boiling causes ice to form over the surface of the bubbling water. Lowering the pressure can cause boiling and freezing to take place at the same time. This must be witnessed to be appreciated. Frozen bubbles of boiling water are a remarkable sight. So what happens is this. If you reduce the atmospheric pressure, i.e. that is the pressure inside the bell jar, if you reduce it completely, you will lower the needed vapor pressure for the material to boil. So the pressure and temperature are proportionate, direct to one another. So if I lower the vapor pressure I need, because it's when the vapor pressure equals the atmospheric pressure. So at 1 atmosphere, I have to heat it to 100 degrees Celsius. But when that's near 0, or as you saw on the triple point diagram, below 610 pascals, the amount of heat needed to raise the vapor pressure of the water so that it's even with that of the atmospheric pressure will be very low. So I'm going to have to use very little heat. So as a result, the water will boil at an extremely low temperature, around freezing. So you have ice forming, ice crystals forming, as well as the boiling process that's going on. So interesting, very interesting phenomena. So I don't believe we have the equipment to pull that off in school, but we will try to do that when I come back, or when we come back. Here's another common misconception. Boiling is a warming process. When a substance cools, the molecules having the highest kinetic energy escape. This lowers the average kinetic energy of the molecules of the substance. The substance then has a lower temperature than it would have had if those molecules had not escaped. So the common misconception is that boiling is a warming process, and indeed it is a cooling process. Condensation, on the other hand, is a heating process. You just have to make sure you understand which way the heat's going. Cooling and heating. So, just think of hot and cold, and what is the perspective, and what is the direction of the energy. Now, the next one will answer the question earlier in the video. Why does hot water freeze faster than cold water on a cold winter's day? And it has to do with this flow of energy. Okay, it has to do with this flow of energy. And this will amaze a lot of you, I think, and it will answer questions that many of you have had relative to this phenomenon. Suppose 4 grams of boiling water are spread over a large surface so that 1 gram rapidly evaporates. If evaporation takes 540 calories from the remaining 3 grams of water and no other heat transfer takes place, what will be the temperature of the remaining 3 grams? What will be the remaining temperature of the remaining 3 grams? Well, here's our diagram that we see very clearly. Well, it's going to take place in 3 parts. Remember, it's boiling water, right? So it's at the 540 mark there. It's to the right of the 540. The first gram takes 140 calories, 180 calories per each of the other 3 grams. So the other 3 grams, if this is going to evaporate, it's going to take 540 calories. That's the first gram is going to take 540 calories. That's 180 each. Well, the second, third, and fourth lose 100 calories. That brings it down to 0 degrees Celsius. And then second, third, and fourth gram lose 80 additional, which brings them to 0 degrees Celsius. So you've seen videos on the web where you throw hot water into the air and it instantly turns to ice and snow. Well, this is why that happens. The boiling water is boiling water, so liquid form, at 100 degrees Celsius, very close to that, very close to the heat of vaporization mark. So this is how that happens, and nothing new, but you should know this for the quizzes. The quizzes will get a little bit difficult, and this will be part of that process. Next slide illustrates the same general principle, but what we're doing is we're going to say what is the minimum amount of 100 degrees Celsius steam required to melt 1 gram of 0 degrees Celsius ice. So you're going from look at the plateau for the 540 calories, that horizontal structure there where it says vaporizing. So you're going to give up 540 calories, and then continue to the left, and you're going to give up another 100 calories for that. So what you want to do is you want to melt. So you're going to go to the right of the melting where it says melting. So you're going to go to the right of that, because 1 gram of ice is just to the left of that plateau, and then 1 gram of water at 0 degrees Celsius is going to be needed. So it's going to be 80 calories over 1 gram equals 640 over x grams. So the amount of heat needed, 640. So I'm going to need 0.125 grams of steam in order to melt that 1 gram of ice from solid 0 degrees Celsius to liquid 0 degrees Celsius. Okay, so that's a problem. You're going to, things are going to get more complicated with this type of problem. So these are all problems that you're going to have to do, and that you're going to be able to do them well. To take this one more step, let's look at firefighting. In firefighting, it says firefighters regularly enter burning buildings to save lives and property. In order to perform their job effectively and safely, firefighters must be knowledgeable about the physics of heat. The most common fire control is dousing a flame with water. In some cases, a fine mist is more effective in quenching the fire. Well, because that mist is going to turn right to steam. And where is it going to get the energy to turn to steam right away? Well, it's going to get it from the fire. So the more energy you can take with the fire, the more water vapor you can make out of the liquid steam, the more effective the firefighting will ultimately be. So it's a function of the amount of steam that you are creating with the fire, and the fine mist will do that better. Well, again, because the fine mist readily turns to steam, and in so doing quickly absorbs energy and cools the burning material. Properly dealing with the flame saves lives, including their own. This is the most important person in a fire is the fireman. If the firemen are not safe, then they can't do their job. And so this way of fighting fire, fighting it with a fine mist, is a much safer way than dousing it with a giant stream of water. Now, you'll notice that if you see films of a plane coming in to douse a forest fire, that plane load of water will turn to a mist right away, and that way it'll turn to steam very quickly. To firefighters, the physics of heat is more than a classroom assignment. It's a matter of staying alive. Job opportunities exist for firefighters with city and county fire departments, and the National Forestry Service will also do that if you want to look into careers in firefighting. It's kind of exciting. There are students at our school that are firefighters locally, and I've had many students in the past who have been firefighters, and some of those students have been the most curious about this whole idea of fighting fire with a mist, as opposed to a giant stream of water where you're just wetting everything. Well, that works in a sense because it's going to drown the fire, but other than that, the mist is better. This is a boiling. Looks at boiling a little bit. Boiling, like evaporation, is a process that cools the liquid left behind. Heating water is one thing. Boiling is another. When 100 degrees Celsius water at atmospheric pressure is boiling, heat is taken away as fast as it is added. That's why it stays at 100 degrees Celsius. The figure shows the water is being cooled by boiling as fast as it is being heated by energy from the heat source. If cooling did not take place, continued application of the heat to the pot of water would result in a continued increase in temperature. So if you think about the process of boiling, it's going to be very clear to you that it is actually the process of boiling, not the process of heating of water, but the process of boiling. You must be taking energy away. If you take energy away, then the water will cool. As the water cools, energy is taken in. So that one sentence there says, if cooling did not take place, continued application of heat to a pot of boiling water would result in a continued increase in temperature. So this is very important for the next couple of slides relative to evaporation. Okay, boiling is a very accelerated form of evaporation. Okay, it's a process that cools. Now, if you're an athlete or you've sweat at all, you'll notice how this can be a cooling process. Here's the athlete, and you produce sweat all over the body, and the sweat evaporates, and the way that evaporates is it takes heat from the athlete, and their body temperature falls. So after you have run a mile or something, you'll see that you can actually get shivery if you stand around. You got to put something on. You got to wrap yourself with something in order to not to lose too much energy. Because if you've ever been to the beach and you get out of the water, you'll notice that you'll get very cool, because the water that's on your body is going to evaporate from the wind, and it's going to get energy from your body, and your body temperature will fall. And if your body temperature falls too much, you can start to shiver. So it's always important to make sure that you're warm after you exercise. A refrigerator's cooling cycle is a good example of the energy interchanges that occur with the changes of phase of the refrigeration fluid. The refrigeration fluid is not water. The liquid is pumped into the cooling unit. Okay, you see the pump down below. Okay, and where it is forced through a tiny opening to evaporate, and it draws heat from the things stored in the food compartment. The gas is then directed outside of the refrigerator and the cooling unit to capture the outside the cooling unit to coils located in the back. Okay. As the gas condenses in the coils, appropriately called condensation coils. So before we continue, just make sure that you understand that you're transferring the heat from one place to another. You're transferring the heat from one place to another. So when the material goes into the refrigerator, it will turn to a vapor. And the only way it can turn to a vapor is if it has heat. And the only place it's going to get the heat, because it's inside the refrigerator, is from the food that's inside the refrigerator. So then it will go on the outside and then recondense and lose that heat. How do you know it's condensing? How do you know there's heat there? Well, because it feels hot. If you look at the back of your refrigerator and feel the air coming out, it's hot air. All right. The heat is given off to the surrounding air. The liquid returns to the cooling unit, and the cycle continues. A motor pumps the fluid through the system, where it enters the cyclic process of vaporization and condensation. The next time you're near a refrigerator, place your hand near the condensation coils in the back or the bottom, and you will feel the heat that has been extracted from the inside of the refrigerator. Another place to feel this is at the back of a air conditioner. It's the same idea. You can hear that condenser in the air conditioning as well. If you sit by a refrigerator long enough, you'll hear the condenser turn on. And what that means is that the cycle is starting all over again, and the freon, the fluid, is being is being pumped into the refrigerator and being allowed to evaporate. And again, it's evaporating, it needs heat to evaporate. And it's getting that from the refrigerator. So nothing's perfect, so you're going to, maybe need some added Freon in your refrigerator sometime in its lifetime. So it doesn't mean your refrigerator is broken, it just means that you're replacing the coolant fluid in order to maintain the efficiency of the refrigeration system. So a very, very important application of the cooling and evaporation, two rather important physical properties of matter. Okay, here are the objectives concerning thermodynamics. Describe what happens to the temperature of a substance when the thermal motion of the atoms approaches zero. State the first law of thermodynamics. Describe the effect of adiabatic compression on a gas. State the second law of thermodynamics. Explain how the second law applies to heat engines. Describe what happens to the orderly state of any natural system. Describe what happens to the entropy of any system. We will also look at the third law of thermodynamics. That's very, very important. It doesn't, for whatever reason, it's not in this textbook, but we will discuss, and I will hold you responsible for the third law of thermodynamics. The common misconception: all the molecules of a substance at a certain temperature have the same energy. Fact: temperature is a measure of the average kinetic energy of the molecules. Some molecules will have more or less kinetic energy than this average. So that's kind of interesting. It's kind of on your test. Temperature is a measure of the average kinetic energy of the molecules. So when you see a temperature of something, not every molecule is at that temperature, but every molecule has an average temperature that is shown on the thermometer. So you have to know the three laws of thermodynamics. So that's very, very important. Now, the next slide, I'm going to take another break, and the next slide that you see will be something that's right out of the book, but I'm going to have it sideways, so it's going to be a little bit difficult to read, but I know you can do it. Okay, as you can see, a sample, let's look at the problem first. A sample of hydrogen gas has a temperature of 0 degrees Celsius. If the gas is heated until its molecules have double their kinetic energy, the gas has twice the absolute temperature. What will be its temperature in degrees Celsius? Well, you can't double 0. So I put this problem here to illustrate how when you're doing this type of problem, you have to convert to Kelvin and then convert back. You got to convert to Kelvin and then convert back to Celsius. Now, this, if you see to the far left, that's absolute 0, negative 273, actually 273.15, but hey, 273 is close enough. And you can see that helium boils at 273. So the question would be, does it form a solid? That's a good question. That's another extra credit problem to tweet me. What is the freezing point? What is the temperature at which helium forms a solid? Okay, or does it have one? Okay, so you're going from left to right. You can see that room temperature is very, very near the bottom of this graph, and that a hydrogen bomb is 100 million Kelvin. So this just shows the variation in temperature depending upon the particular physical setting. The next thing we're going to look at is we're going to look at joules, the Joule apparatus. Okay, let's spend some time on this. you have the paddle wheel apparatus first used to compare heat energy with mechanical energy. As the weight falls, they give up potential energy and warm the water accordingly. This was first demonstrated by James Joule. It's an actual person for whom the unit of energy is named. First of all, the unit of energy is unit of mechanical energy is named a joule. And this apparatus, the idea of whipping up the water to make it warmer, is not something that was very well known. I mean, the conversion, the heat energy needed to raise the temperature of water. The mechanical energy is not raising the temperature of the water, essentially. I mean, it certainly is by converting the mechanical energy to heat energy, and the mechanical energy is actually transferred to the molecules, so there is movement still there. But we consider the energy that is produced mechanical energy, and the energy that is absorbed by the water to be heat energy. You can see, because you're increasing the motion of the molecules, you can see that this transfer of energy, there's a connection between mechanical energy, joules, and heat energy, calories. So there's a connection between the two, and I can have a conversion factor as a result of that. All right, this next slide is full of a lot of information, so let's take it one step at a time here. On the left, upper left, it says common misconception: the vast internal energy of bodies like the ocean can be converted to useful energy. Fact, it is not possible to convert a given amount of heat into mechanical energy without external effort. Common misconception: a friction-free heat engine would be 100% efficient. Would be a 100% efficient engine. Fact: even without friction, a heat engine can only convert some of the heat input to work. Okay. Critical thinking. Explain how the second law of thermodynamics tells us that it is impossible to produce usable energy with zero environmental impact. Heat engine will increase its internal energy by absorbing heat from a reservoir of higher temperature, convert some of this energy into mechanical work, expel the remaining energy as heat to some lower temperature reservoir and gasoline engine. The burning fuel in a combustion chamber is the high temperature reservoir. Mechanical work is done on the piston. The expelled energy goes out as an exhaust. Very full of information there. We're gonna look at that one step at a time in the next couple of slides. I'm not actually telling you necessarily what the first and second law is yet, but we will come up with a summation of all the stuff that we're doing in this particular idea. Well, first of all, you have an engine. We have the high temperature is where the explosion takes place in the piston chamber, producing work, and then the excess energy that's not used is put in the low temperature pan or blown out the muffler. And you know that the muffler is very hot, so a lot of the energy is not even going into work. Here I have a piston on the left. It says a mixture of fuel and air is burned rapidly in a combustion engine to push a piston in the engine that is in turn propels the vehicle. In a jet engine, a mixture of fuel and air is burned rapidly, and instead of pushing pistons, pushes the aircraft itself. Which do you suppose is more efficient? The jet engine. A jet engine, it saves a step, so it's more efficient. next extra credit. Explain to me a little bit further how a jet engine works relative to this, where you're, reducing one of the steps instead of the piston being some mechanical object as is on the left, where the piston's going up and down based on the rotor, and the rotor's turning the wheel, and it's, the hand bone is connected to the arm bone, etc. Do a little bit of research on the jet engine and see if you can put it in your own words, if you can email me at tdarcy17@gmail.com, if you can actually tell me a little bit more, put it in your own words, what a jet engine is relative to this slide, where instead of the piston being some mechanical object, it's in actuality the plane on this. Okay? Let's take another break, and I'll be right back. Have a great day, and take care. Okay, adiabatic process, Greek for impassible. When a gas is compressed or expanded so that no heat enters or leaves a system. Changes of volume can be achieved by performing the process rapidly so that heat has little time to enter or leave, or by thermally insulating a system from its surroundings. For example, polystyrene foam, otherwise known as styrofoam. So you are expanding and contracting very quickly. The faster that you expand and contract, the more adiabatic the process is going to be. So when we look at the next few slides, especially the engine one, keep in mind that adiabatic is very difficult to achieve. Fuel cells in electric vehicles, one of the attractions of fuel cells and of electric vehicles in general is that they are not heat engines. Their efficiencies are not limited by the Carnot cycle constraints of the second law, while the efficiency of an engine that burns or combusts fuel will always be limited by the temperature difference between the cylinders and the exhaust. Fuel cells and batteries have no such thermal constraints. Fuel cells running on pure hydrogen can be as much as 80% efficient in converting chemical energy to electrical energy. Watch the growth of fuel cell technology and electric automobiles. If I were young, if I were your age, and I know what I know now, I would take whatever money I could find and invest it in fuel cells. Can you imagine if all the cars on the road were suddenly converted to engines with fuel cells? It would be unbelievable, absolutely unbelievable. The combustion engine would become a dinosaur, a giant dodo bird. And does this already exist? And I ask you this question. If it does already exist in limited fashion, why doesn't it exist in a greater fashion? And is the answer to this question, does it involve oil companies and those companies protecting their livelihood by buying patents and sitting on them? That's a good question. Adiabatic compression and expansion of gases in the cylinders of an automobile engine. This is where things get a little bit inefficient. Compression expansions occur in only a few hundredths of a second. This is too short a time for appreciable heat energy to leave the combustion chamber. For very high compressions like those of diesel engines, the temperatures achieved are high enough to ignite a fuel mixture without the use of spark plug. Diesel engines have no spark plugs. So this is another extra credit. What's more efficient, diesel engine or regular combustion engine with spark plugs, and why? So tweet that to me. That's a short tweet, and let me know which one has a higher efficiency, and do the spark plugs make a difference in the efficacy of the engine? All right, the next slide, we're going to look at a five phases of a combustion engine with the piston. Okay, it says A, fuel air mixture fills the cylinder as the piston moves down. B, the piston moves up and compresses the mixture adiabatically since no heat transfer occurs. C, the third step in the middle, it says the spark plug fires, ignites the mixture, and raises its temperature. D, adiabatic expansion pushes the piston downward, the power stroke. E, the last one, the burned gases are pushed out the exhaust valve, and the cycle repeats itself. How do you know that this adiabatic, by this happening very quickly, is not particularly adiabatic? Well, the engine gets hot. You can feel it on the outside. That's waste energy. So you can tell if something is truly adiabatic by, is heat leaving the system? Okay, you've all pumped a tire up. Do work on a pump by pressing down on the piston, and the air is warmed. When a gas is compressed or expanded so that no heat enters or leaves the system, the process is said to be adiabatic. Adiabatic changes of volume can be achieved by performing the process rapidly so that heat has little time to enter or leave, as with the bicycle pump in figure 24.3, or by thermally insulating the system from its surroundings with polystyrene foam, for example. Polystyrene foam is styrofoam. So you can see very clearly that there's something odd going on here. What does it mean? I want you to email me some kind of understanding of this by saying when a gas is compressed or expanded so that no heat enters or leaves the system, the process is said to be adiabatic. Adiabatic changes of volume can be achieved by performing the process rapidly so that heat has little time to enter or leave the system. Fairly interesting, and see what that means. That's a very important sentence. Those first two sentences there. This whole slide, actually, in terms of being confusing. The next is, as you may have done this lab in chemistry, where you take, it says a mass of air is contained so that the volume can change, but the pressure remains constant. Table 1 shows air volumes at various temperatures when the air is heated slowly. Plot the data in table 1 on the graph and connect the points. Okay, so you can see that there's the experimental model is on the left, and I am determining the volumes based on the temperature, and I just simply plot those points. Now I'm extrapolating back across the y-axis, and I see that the graph intersects the temperature axis at absolute zero. Now scientists use Kelvin instead. So if I was going to convert Kelvin to the degrees Celsius to Kelvin, I would have this graph starting from 0, and it would look like that. And it says, in the question, it says, scientists measure temperature in Kelvin instead of degrees Celsius, where the absolute zero of the temperature is in Kelvin degrees, 0 Kelvin. If you relabeled the temperature axis on the graph in question 1 so that it shows temperature in kelvins, would your graph look like the one below? And the answer is absolutely. Okay, so remember, we don't use Celsius when we're doing these types of problems because it can't be in the denominator. When work is done on a gas by adiabatically compressing it on the right, if you look at the right of this, the gas gains internal energy and becomes warmer. When a gas adiabatically expands, it does work on its surroundings and gives up internal energy and thus becomes cooler. So your finger is the blue. So if your finger gains internal energy, it's going to feel warmer. It's going to be warm. And again, the blue circle is your finger, and if it cools or work is done on the outside, on the environment, then it's going to feel cool. So it's all about perspective. The black surroundings is where the work is either going to or coming from in order to change the system. The next we've looked at before, blow warm air onto your hand from your wide open mouth. Now reduce the opening between your lips so that the air expands. It expands, adiabatic expansion. The air is cooled. So that's a very simple example of what we're talking about here. You know the air is expanding because it's compressed in your mouth and you're forcing it through, and you're reducing the pressure. If a blob of air initially at 0 degrees Celsius expands adiabatically while flowing upward alongside a mountain, a vertical distance of 1 kilometer, it will reduce temperature -10 degrees. Every kilometer, that cloud is going to either increase or decrease by 10 degrees, depending upon if it's rising or falling, if it's expanding or contracting. When it rises 5 kilometers, it will be -50 degrees Celsius. Now this should be relatively shouldn't be relatively new to you because you read the book, but the point is that it's going to either adiabatically expand or contract. Now, for instance, if I have a giant dry cleaner bag full of air at a temperature of -35 degrees Celsius floating like a balloon with a string hanging from it 10 kilometers above the ground, estimate its temperature if you were able to pull or yank it suddenly to the Earth's surface. So instead of a dry cleaner's bag, I have a balloon, and I'm going to bring it down, and it's obviously going to compress. You're going to compress it, so it's going to be 10 degrees per kilometer of descent. So it's going to warm by 100 degrees Celsius, -35 degrees Celsius warms by 100 degrees, and it's going to be 149 degrees Fahrenheit, or 65 degrees Celsius. So that's what happens. That's what happens in weather when masses fall from a height. For instance, weather, and we'll look at that in a minute. But very important set of slides. Helium has a special property that its internal energy is directly proportional to its absolute temperature. Consider a flask of helium with a temperature of 10 degrees Celsius. If it is heated until it has twice the internal energy, what will its temperature be? So you're going to, it has to have twice the internal energy. So it's going to be, you got to change it to 283 Kelvin, and then multiply it by 2, and that's going to be 566, or 293 Celsius. So it's going to go from 10 degrees Celsius to 293 Celsius. So it's quite an increase. But again, you want to convert it to Kelvin. Now, this is the western United States, where you have this warm, moist coastal air from California rising over the mountains, and then it's going to fall down the side of the mountain and be adiabatically compressed. Therefore, the Chinook warm, dry winds occur when high altitude air descends and is adiabatically warmed. So that's the Chinook. You may have heard the Chinook out west. The Great Plains stay warm-ish in the winter sometimes, depending upon the flow of air. The temperature of a blob of air that adiabatically expands adiabatically, changes by about 10 degrees Celsius for each kilometer of elevation. Again, a wonderful weather analogy. So the Chinook winds, comes the blob of air 4 kilometers up in the mountains, descends down to the mountains. So you're going to come down 4 degrees, and that's why you're going to warm the land, because this cold mountain air is descending and is being adiabatically compressed. So when you adiabatically compress a gas, it's going to become warmer. All right? So next, we have some more weather that we're going to look at. It says a dramatic example of adiabatic warming is the Chinook, a wind that blows down from the Rocky Mountains across the Great Plains. Cold air moves down the slopes of the mountains, is compressed by the atmosphere into smaller volume, and is appreciably warmed. In this way, communities in the paths of the Chinooks experience relatively warm weather in midwinter. The effect of expansion or compression on gases is quite impressive. It can even create enormous thunderheads, a giant cloud formation down from the mountains, and warms the Great Plains. I was talking to someone on the phone in Utah, and it was mid-70s and mid-40s in New Jersey. So, this whole concept of weather and Chinooks and et cetera, first of all, you must understand that weather flows from west to east in North America. So the concept of the Chinook wind is very important to understand our weather, especially in that part of the world, like for instance in Nebraska, but also the idea of adiabatically compressing a gas or expanding a gas. Now, the rest of the unit will talk more specifically about the thermodynamics, the laws of thermodynamics. We're going to talk about Carnot efficiency next. And Carnot efficiency looks at the engine that we were looking at earlier. We're going to go back to the engine. We took a little break from the engine to talk about adiabatic. And the Carnot efficiency, or ideal efficiency, equals the temperature of the hot sink minus the temperature of the cold sink divided by the temperature of the hot sink. So you can see that the greater the difference in the temperature between the hot and the cold, the better the ideal Carnot efficiency will be. Okay, so let's look at this. We're going to do several problems on Carnot efficiency, where I'm going to give you the hot and cold sinks, and you're going to tell me what the ideal efficiency is. Again, we don't really use percentages. We certainly can, but we're going to use decimals instead, so not to worry about that. T must be in Kelvin, 0 cannot be in the denominator. Okay, here we go. So T hot and T cold, those are the sinks, are expressed in kelvins. For example, when a hot reservoir in a steam turbine is 400 Kelvin and the sink is 300 Kelvin, the cold sink is 300 Kelvin, the ideal efficiency is 300, 400 divided by 300, divided by 400 is going to be equal 1/4 or 25%. This means that even under ideal conditions, only 25% of the internal energy of the steam can be converted into work, while the remaining 75% is expelled as waste. This is why steam is superheated to high temperatures in steam engines and power plants. The higher the steam temperature driving a motor or turbo generator, the higher the efficiency of power production. Increase operating temperature in the example 2, 600 Kelvin yields an efficiency of 1/2, twice the efficiency of 400 Kelvin. So again, quite dramatic when it comes to efficiency. You're heating this instead of the 400 to 600, and then subtracting 300 divided by 600 is 1/2. So you're doubling the efficiency of the engine by increasing the heat of the hot sink to hot reservoir to 600 Kelvin. Okay, what is the ideal efficiency of an automobile engine wherein fuel is heated to 2700 Kelvin and the outdoor air is 300 Kelvin? Well, very simple. 2700 minus 300 divided by 2700 is 0.89, and that's the ideal efficiency, or simply 89%, which people might find a little bit better to say. A modern electric power plant, though large and complex, can be approximated as a simple heat engine. The power plant uses heat from the burning of coal, oil, gas, or heat from nuclear fission to do work turning electric generators. In this process, it also produces waste heat as an inevitable consequence of the second law of thermodynamics. This waste heat is sometimes called thermal pollution, because like chemical waste, it pollutes the environment. Now, if any of you have ever traveled and seen these absolutely gargantuan mammoth giant cooling towers, these are just not for nuclear. This is for any cooling tower, for any power plant, be it gas or nuclear. You get these giant, absolutely or horrendously big power plants, and they contribute to the thermal pollution. Waste heat discharged into waterways can raise temperature of aquatic environments enough to kill organisms and disrupt ecosystems. Waste heat discharged into the air can contribute to weather changes. Thermal pollution is unlike chemical pollution, since chemical pollution can be reduced by various methods. The only way to manage thermal pollution is to spread waste heat over large enough areas to absorb it without significantly increasing temperatures. Conservation and efficient technology are absolutely crucial to the health of our planet. Critical thinking explain how the second law of thermodynamics tells us that it is impossible to produce usable energy with zero environmental impact. Okay, so that might be a question for you, and here we are. It says, explain how the second law of thermodynamics tells us that it is impossible to produce usable energy with zero environmental impact. All energy transformations produce waste heat, and waste heat pollutes the environment. It's as simple as that. You're going to have a transformation, an energy transformation. you're going to produce waste heat, and there is absolutely nothing you can do about it. So here I have the power plant, the guts of the power plant. A steam turbine turns because high temperature steam from the boiler exerts more pressure on the front side of the turbine blades than the low temperature steam exerts on the back side of the blades. Without a pressure difference, the turbine would not turn. And you can see you're going from 5 atmospheres, that's the high pressure, that's the high pressure 5 atmospheres, high temperature 600 Kelvin, and when after it passes over the blades, it's going to drop to 1 atmosphere, and 5 atmospheres, 5 atmospheres over 600 Kelvin, and then 1 atmosphere over 100 Kelvin. So it's going to be pretty significant in you're going to go from 621 degrees Fahrenheit to negative 279 degrees Fahrenheit. So, you know, the greater the temperature difference between the hot and cold sink, the greater the efficiency of the matter. So if you look at that, that's a general schematic of what happens in a power plant. There are differences depending upon whether or not they are fossil fuel or nuclear, but by and large, you're using a fuel to boil water. Continuing with this, heat engines, we can see the role of temperature difference between heat reservoir and sink in the operation of the steam turbine engine in the figure on the prior page. Notice it says between the heat reservoir and sink. They're both reservoirs or they're both sinks. It really doesn't matter. You can have a heat sink, heat reservoir. Okay, steam from the boiler is the hot reservoir or hot sink, while the sink is the exhaust region after the steam passes through the turbine. I use them interchangeably. I may not be correct, but I really don't care. The hot steam exerts pressure and does work on the turbine blades when it pushes on their front sides. This is nice, but steam pressure is not confined to the front side of the blades. Steam pressure is also exerted on the back side of the blades. Counter-effective and not so nice. A pressure difference across the blades is vital, for it causes the turbine to keep spinning, allowing it to do work. If pressures were the same on both the front and the back, no work would occur. So again, very important. You might want to put this on pause and go back and look at the drawing. So we have the heat reservoir and the exhaust sink, or they call it the exhaust sink or cold sink. Cold sink, hot reservoir is what the book is saying. So looking back on this, we can see that this is only efficient if there are a difference, or there is a difference between the hot and the cold. Okay, let's look back at this, and we see that because there's, you're going from 5 atmospheres, 600 Kelvin, to 1 atmosphere, 100 Kelvin. So you're dropping the temperature. So you're comparing 600 Kelvin with 100 Kelvin when you're determining the efficiency. So you could determine the efficiency by saying, essentially, 600 minus 100 divided by 600 is going to be pretty efficient. But again, you have to make sure that that there is a large temperature difference in this whole process. Okay, I'm going to take another break, and you should too. We'll be finished momentarily. We got a little bit more to do, but you should be taking notes on this. And again, not doing this all in one sitting. This is a picture of my home in Wall Township. The roof is the butterfly look. But seriously, this is just an example of entropy, increasing entropy. Entropy is called disorder. The entropy of any system will happen spontaneously by itself. The entropy of the universe is increasing. You can see by this next slide, the top, if the particles represent gas molecules at normal temperatures inside a closed container, which of the illustrated configurations come first? Well, it would be the one on the right and then the one on the left. So, you're increasing entropy. If you tossed bricks off a truck, which kind of pile of bricks would you more likely produce? Well, the crazy one. This is ice melting, and you are increasing entropy. So when something melts, it increases entropy. So going from left to right, you are maximum entropy, minimum order. Here's another one where, like the Big Bang, all of the little particles are tightly crowded together, and they do not really look it. Given the chance, the particles spread out as much as possible. This increases the entropy. Entropy is pleased. So entropy is the tendency to increase. There's two driving forces in nature: decreasing internal energy and increasing entropy. Those are the only two that exist. First law, the law of conservation of energy applied to thermal systems. The first law states that whenever heat is added to a system, it transforms to an equal amount of some other form of energy. So that's the law of conservation of energy applied to thermal systems. First law. Now, the second law, the direction of heat flow in natural processes. The second law states that heat will never of itself flow from a cold object to a hot object. According to the second law, the entropy of a system always increases for natural processes. Okay, that is the second law. So the second law has to do with entropy. The next, as the thermal motion of atoms in a substance approaches zero, the kinetic energy of the atoms approaches zero, and the temperature of the substance approaches the lower limit, or 0 Kelvin. And that's the third law. That's not in the book, but it's something you have to know. These three laws may seem obvious to you, but hundreds of years ago they were anything but obvious. They really didn't know which one was which or how they changed. Now, these are problems right off your problem 11, problem set 11. Finishing his ginger ale, Ramesh stands at a party holding his insulated foam cup that has nothing in it but 0.100 kilogram of ice at 0 degrees Celsius. How much heat must be gained by the ice in order for all of it to melt? So you have 0.1 kilograms of ice at 0 degrees Celsius. How much heat is gained in order to melt it? So you go from 0.1 kilograms of ice at 0 degrees to 0.1 kilograms of water. So how much, what's the story with this? Okay. Well, this is actually very simple. You probably have already solved it. It's going to be the mass, 0.1, times the heat of fusion. Now, this heat of fusion is in joules. You could have said calories or kilocalories, but this is going to be 335,000 joules times 0.1, and that's going to be 33,500 joules. Is going to be the answer to that problem. Notice I'm using joules per kilogram instead of calories per kilogram. That's very important. Or even kilocalories per kilogram. So Make sure you know what you have. I will tell you how to, I'll tell you before you solve these problems, I'll let you know what you need in the solving of these. The village blacksmith dunks a red hot horseshoe into a large bucket of 22 degrees Celsius water. How much heat was lost by the horseshoe in vaporizing 0.0100 kilograms of water? So when you're saying you're vaporizing it, you're simply increasing to 0 degrees Celsius to 100 degrees at gas. So the answer is obvious there. It's the amount of heat needed to raise the temperature to 100 and then the heat of fusion. So it's going to be 2.59. Okay. Next, by January, the 3.0 kilograms of water in the bird bath in Robin's backyard has frozen to a temperature of -7 degrees Celsius. As the season changes, how much heat must be added to the water to make it a comfortable 25 degrees Celsius for the birds? So it's got to, first of all, you've got to change it. You got to change it to ice at 0 degrees. So that's the first heat, 3 times 7 degrees times 2090, and then you're going to heat that up. You heat of fusion and then add to it the amount of heat needed for 25 degrees Celsius, and that's going to be 1.4 times 10 to the 6 joules. Okay, and next problem. In a physics experiment, a 0.100 kilogram aluminum calorimeter cup holding 0.2 kilograms of ice is removed from a freezer where both ice and cup have been cooled to -5 degrees Celsius. Next, 0.05 kilograms of steam at 0 degrees Celsius is added to the ice in the cup. What will be the equilibrium temperature of the system after the ice has melted? So this is going to be a very involved problem. I'll let you work this problem out. I'm not going to really say much. I'm just going to sit back and watch it happen. So I'll say goodbye for now and take care. Good luck on this problem. There are the given constants, for instance, and take care. Just to let you know, hopefully you're still watching this, that this will be a quiz, this specific problem actually. Different numbers, of course, will be a quiz. It's rather lengthy, so it might be a good idea to take careful notes relative to this problem. I will let you know specifically what the heat of vaporization, heat of fusion, and specific heat capacities will be in. In here, they're relative to joules. However, I might make it in calories. So there may be different numbers altogether. So, practice this problem with calories and with joules. Okay? Okay, so you can see that the final temperature is 56.5 degrees Celsius. All right, well, I'll see you tomorrow in school, and goodbye.